Welcome to The Explainer, where we take those deeply complex technical guides and transform them into clear, actionable architectural insights. Today, we're unpacking a really fundamental concept straight out of Ash Allen's comprehensive guide on consuming APIs. If you've ever found yourself wondering how completely different systems across the web manage to talk to each other so securely and efficiently, well, you are definitely in the right place. Let's dive in.
Seriously, think about it for a second. How do modern web applications seamlessly integrate things like credit card payments, or send automated SMS messages, or pull in massive, complex datasets without their developers having to build every single piece of that infrastructure from absolute scratch? It would take lifetimes.
The secret is the API, or Application Programming Interface. Think of it as a universal translator for the web. An API allows your application to delegate all that heavy lifting to someone else. For instance, you absolutely do not want to deal with the massive headache of highly regulated security rules, like PCI compliance, just to process a credit card. Instead, you just send a quick request to a service like Stripe. The API translates your request, Stripe handles all the terrifying compliance and processing, and then they just send back a clean API response. You don't need to know a single thing about the inner workings of their system.
But here's the really cool part. APIs aren't just for hooking into third-party tools on the outside. They are absolutely perfect for separating your own internal architecture, too. You might have a customer-facing website and a totally separate employee admin panel. By having them communicate through an internal API, you keep those systems completely independent. If you totally overhaul how the customer website works, your admin panel doesn't randomly break because it's only ever interacting with that stable API bridge.
All right, moving on to Section 1, Data Formats. Essentially, the languages of APIs.
Before these isolated systems can actually talk, they have to agree on a language to structure their data. And we have a fascinating trade-off here between the two most common formats, JSON and XML. On one hand, JSON is the undisputed lightweight champion. It offers native efficiency with JavaScript, which means smaller file sizes and blazing fast speeds. But it doesn't have native schema validation, and you can't even leave comments in the code. On the other hand, we have XML. XML is much more verbose and self-describing. It kind of looks like HTML. But because it offers strict XSD schema validation, you can mathematically prove a request is structured perfectly before it ever even gets sent over the network.
Let's jump into Section 2, the messenger. We're going to look at the actual anatomy of an HTTP message. So how are these JSON or XML formats actually delivered across the web? Well, every single HTTP message boils down to three anatomical parts. Think of it literally like mailing a package. Step 1 is the start line. That's your shipping address, dictating the exact action, like telling the server to post data to a very specific URL. Step 2 contains the headers. This is vital context, providing things like your authorization API key, or just telling the server, hey, the content type inside is JSON. Finally, step 3 is the body. That's the box itself carrying the actual data payload, like the specific name and email you're trying to save. And when that package arrives, APIs use a standard cheat sheet of status codes to instantly tell you what happened. A 200-level code? That's a high five. Complete success. Your request was accepted. A 400-level code means a client error. That means you messed up. Maybe you're unauthorized. Or you hit the infamous 404 not found. And if you see a 500-level code, that's a server error, which means their servers are currently having a really bad day.
Which brings us to Section 3, the standard. Time to decode REST architecture.
So, how do we organize all these messages systematically? Enter REST, which is by far the most common set of rules for API design today. But to be truly RESTful, an API has to follow some pretty strict constraints. It separates the client and server. It uses a layered system, meaning you don't actually know if you're hitting the server directly or just a load balancer. It allows for cacheable responses to save bandwidth. But the absolute most crucial rule, it must be stateless. The server remembers absolutely nothing about you between requests. Every single ping you send has to carry all the context necessary to be understood in total isolation.
Now, one of the most powerful concepts here, and definitely the longest acronym, is HADOS, Hypermedia as the Engine of Application State. It's brilliant. It elegantly allows your client to navigate the API without hard-coding a bunch of external URLs. Instead of just handing you a user's ID and forcing you to guess the URL to find their blog posts, the API response directly provides dynamic links to those related resources. You can programmatically navigate the API exactly like you'd click hyperlinks on a normal web page. But the web didn't stop there. Let's look at Section 4,
The evolutions, overcoming REST's limitations.
As applications grew massive and started scaling globally, developers began hitting the limits of the REST architecture. It kind of forces you into a fetching dilemma. Because REST endpoints are strictly resource-based, you often overfetch. You might download a user's entire megabyte-sized profile when literally all you needed was their first name. Or you underfetch, forcing you to make multiple, slow round trips to the server just to piece together a user and their posts. GraphQL totally solves this. It lets you use a surgical scalpel to query exact fields across multiple resources, getting a highly specific, product-centric response in one single request.
To really understand why we have this, let's step back historically. Back in 2012, Facebook was desperately trying to rebuild their native iOS app. They realized their mobile app was literally choking on bloated REST responses. Making multiple requests to load a single newsfeed was just way too slow on 2012 mobile networks. So they invented GraphQL purely to save bandwidth and speed things up. It was so incredibly effective that by 2015, Facebook officially open-sourced it to the entire world.
The absolute game changer with GraphQL is version control. Say goodbye to managing endless broken version numbers in your URLs like v1 or v2. GraphQL uses a single, continuously evolving version based on a strongly typed schema, so you always know exactly what data to expect. You run queries when you want to read data and mutations when you need to write data. And if a field gets outdated, developers simply mark it as deprecated directly within the schema, without breaking the integration for literally everyone else. It's so smooth.
Finally, let's wrap up with Section 5, RPC and Beyond, Action-Oriented APIs.
Let's explore an architecture built purely for raw server-to-server performance. Unlike REST, which is completely obsessed with resources and performing basic CRUD operations on specific URLs, RPC, which stands for Remote Procedure Call, is entirely focused on executing actions. In RPC, you usually just hit a single endpoint. Instead of manipulating a message resource, you just explicitly tell the server to execute a specific procedure, like send message. It treats remote servers almost as if they were just local code functions running on your own machine. Today, this paradigm is heavily popularized by Google's gRPC framework.
Because modern gRPC rides on the HTTP/2 protocol, it unlocks some crazy continuous streaming capabilities that traditional request-response cycles just can't handle. Beyond standard unary requests, you get server streaming for massive file downloads, client streaming for giant data uploads, and my favorite, bidirectional streaming. This is where both the client and the server are continuously firing data at each other simultaneously. It is absolutely perfect for things like real-time chat applications.
So there we have it. We've got REST for your standard, reliable resources, we've got GraphQL for absolute surgical precision, and we've got gRPC for blazing fast, high-performance server actions. Remember, there is no such thing as a perfect API. There's only the right tool for the job. With all of these incredible architectures at your fingertips, are you going to stick to the old standards? Or what are you going to build next? Thanks for joining me on this explainer. Keep learning, keep building, and I will catch you next time.